This video is for the ACE Physical Science 1114. And there's a lot of chemistry in this piece. And there's some really actually challenging things covered in this one. So I'm going to do my best to cover the content on pages 6 through 11 in the reading part of the piece. And that will help you do a few pages in the workbook. I think it's like pages C, D, E, okay? And today I actually have two of my own students who are in this piece and came to me and said, Mr. Anger, we need a video for this piece. So if I'm looking at them and not at the camera, you'll know that I'm looking at my actual live students and trying to help them get ready for an upcoming self-test in this piece, all right? So we're going to cover this, and actually what's cool is I am teaching this very same concept right now in my chemistry class, and I have to tell you that the physical science pace goes through a lot of stuff very quickly that we cover a lot more slowly in our chemistry class. So this is challenging, all right? But let's do it. So one of the first things we want to talk about here is something called valence electrons, okay? Valence, I always call them valence. Maybe it's valence. But the electrons that are in the outer shell of the atom are the ones that can interact with other atoms that are nearby. So just by looking at the periodic table, all of these elements that are in family 1 have, guess how many electrons in their outer shell?
2.
1. In family 2, guess how many electrons they have in their outer shell? 2. This is actually family 3. Now in this periodic table it does not say Roman numeral 3A, but on the one you have in your paces it does say 3A. All of these have 3, 4, 5, 6. These have 7. These are the halogens. You're going to learn about that in this piece. These are the noble gases. They have 8 electrons in their outer shell. Now here's the magic number 8, okay? 8 is the octet rule. If you ever played a piano, an octave is 8 notes. An octopus has 8 legs, okay? So octet means that this is the magic happy place for atoms. They want to have 8 electrons in their outer shell. All of these already have 8 electrons. So argon, for instance, has 8 electrons in its outer shell, and if you look at your periodic table that came with your paces, and you look at the last energy level, you'll see that you count them up. There's 2 plus 6, okay? 2 plus these 6 in energy level 3. He's happy as it is. So just like in some of the movies, the nobility, the nobles, kind of have their nose in the air, and they don't need to have anything to do with the people below them, okay? Because they are satisfied. They have their nice house, they have their carriage, they have their horses, they have their servants, they don't need anybody else. The noble gases are kind of like that. We don't need the other elements, okay? So they stay to themselves. They are the only ones, though, that are happy by themselves. All these others want to have a friendship with some of the other atoms. And again, 8's the magic number, so let's notice something here. All of these have 1 electron. If they can just somehow get rid of that 1 electron, then they'll be happy because the shell underneath is a full shell. These atoms over here, if they can gain 1 electron, will be a very happy atom. And so this is when these atoms here give up 1 and these take that 1 electron. Let me take an example here, Na and Cl, and Na says, I've got 1 electron and I want to get rid of it. So it donates it. Chlorine says, hey, I'll take that electron, and grabs it. Chlorine now has 17 protons, but it gained an electron. So it has 1 more electron. What charge do electrons have?
Negative.
Negative, very good. So chlorine becomes a negative ion. Now you learned in a previous pace, if it's negative, it is an anion, a negative ion, anion. Sodium lost an electron, so it has more positive charge than negative. It is a cation. Don't worry about that. But these two ions are now oppositely charged and opposites attract, and so this forms a very strong bond. This is called an ionic, root word ion, an ionic bond. And I think we actually covered that in a previous pace. But that's one type of bond, okay? These here can give up 2 electrons, okay? These need 2 electrons. So magnesium and oxygen, they just come, one of each comes together. There are other ways we can combine these by giving up electrons, these by gaining, and form these ionic compounds. But what we're talking about in this pace are covalent. Now let's think about what that prefix co means. Have you had that in your etymology yet? The prefix co means? With, together, okay? Valent, the root word, valent means valence. Okay, so the valence electrons are not being completely given up, but they're being shared. So it would be like a kindergartner and a big high school boy both trying to fight over the same ball, okay? And they might both grab onto that ball and not let go. In fact, in your pace, they have a picture. It looks like this, okay? Do you remember this one? Mm-hmm. So here's this big high school boy, and he's grabbing onto a ball. Here's this little guy, he's trying to hold on to the same ball, and that ball is an electron. Now in a basketball game, if they were doing this, the referee at some point would say, jump ball, and then it would go to one team or the other. But if the referee didn't see it and he didn't blow his whistle, they would be locked together, holding that ball and not letting go. And now they have become, okay, together, a pair. That's literally what's happening with these electrons, is if we take, let's say, carbon and oxygen. Well, let's first take hydrogen. Hydrogen and oxygen. Now, hydrogen's over here, but it actually is a nonmetal. So these are metals, but we can take hydrogen as a nonmetal, and we can take oxygen. Now, how many electrons does oxygen have in its outer shell? It is in family 6. Okay, so it's going to have 6 electrons. So I'm going to do 1, 2, 3, 4, 5, 6. I put 2 on the top, 2 on the side, 1 on the bottom, 1 on this side. Now this hydrogen comes up alongside and says, hey, I've got 1 electron I want to share with you. And he says, hey, well, you got a friend? If you got another hydrogen, he can come up on this side and share his electron, and then we'll all be happy. Now, hydrogen is the one exception to the octet rule, because hydrogen is in energy level 1, which only has the s orbital. Remember that? So it can only have 2 electrons. So when it has 2, it's happy. Everybody else wants 8. So oxygen wants 8, hydrogen wants 2. So when hydrogen says, I'll share 1 with you if you share 1 with me, oxygen says, sure, that sounds like a good deal. This hydrogen says, I'll do the same thing. So hydrogen right here is happy. Hydrogen's happy. Oxygen has, count them up, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay? 6 of his own plus the 2 he's sharing. So we would, and I think in the pace they're going to have you do something like this. You can circle a pair of shared electrons. Okay? So those are shared. And in a structural diagram, we can show it like this and then put 1, 2, 3, 4. And if you count them up, and each of these dashes represents 2 electrons. It's kind of like, I picture it as if the 2 endpoints are the electrons, okay? So 1's coming from hydrogen, 1 from oxygen. So there's 1, 2, 3, 4, 5, 6, 7, 8 total around oxygen. Now, why do we do this shape instead of lining them up side by side? I'm glad you asked that question because I want to show you with this model of what an atom, what a water molecule would look like, okay? So I'm going to let this represent the oxygen. And these holes on here represent an electron that's able to be shared. Okay, so it can form a bond at that point. So oxygen has 2 bonding sites, but the other 2 sites are full. They have the electrons are not sharing, okay? That would be these 2 right here, and these 2 right here represent this spot here and this spot here. It's kind of like filled in holes, okay? Hydrogen comes up, and hydrogen says, I want to share one of those electrons and form a bond there. And then let me find another one. Another hydrogen comes up and says, and I'll bond on the other site. And so these 2 sites are full, and now these 2 have hydrogens bonded to them. So actually they're not at a right angle. Technically it's 105 degrees. You don't need to remember that, okay? So a water molecule takes on this shape in 3-dimensional space, okay? Now let's take another atom like carbon. I'm going to put carbon in the middle. Carbon is in family 4, so it has 1, 2, 3, 4. Okay? And what if I want to bond carbon with hydrogen? How many hydrogens would bond with that carbon, do you think?
4.
4?
Yeah.
Very good. So this black one's going to represent carbon, and there's a hole on every side. So I'm going to put one there, and one there. I already have one made here, so I'll pop that one in, and one here. So when carbon with 4 hydrogens bonds together, this is the shape that it takes on. Okay? Now when we draw it on the board, we can't draw it in that way, so we put a hydrogen here, hydrogen here, hydrogen here, hydrogen here, and we put, and then we can draw a line like that and say, okay, the carbon is sharing with 4 hydrogens, but actually in 3-dimensional space, this is more what it would look like. All right? Now, let me show you something interesting, because carbon dioxide. All right, how many electrons does oxygen have again in the outer shell?
6.
Okay. So I'm going to put carbon here with 1, 2, 3, 4. And I bring an oxygen up here and an oxygen up here. Oxygen has 1, 2, 3, 4, 5, 6 electrons. Okay, 1, 2, 3, 4, 5, 6. So I can form a bond here and a bond here. Are they happy? No. Because carbon only has 1, 2, 3, 4, 5, 6. Carbon says, I'm not happy. Oxygen says, and actually I'm not happy. I have 1, 2, 3, 4, 5, 6, 7. So we have a problem still. They need to do something more in order to form a bond. Okay? And what happens is this oxygen says, I'll share this lonely electron down here if you'll share that lonely electron there. And so they form a double bond. And the same thing happens here. This one and this one form a double bond here. Now let's see what that would look like when we put it together. So I'm going to let this, again, represent carbon. And we're going to take 2 of these to represent oxygen. And so now we're going to put these longer ones so we can show what these double bonds look like. And these things move all around. Yay! Isn't that cool? All right, so in three-dimensional space, these double bonds, so carbon now has how many around it? 1, 2, 3, 4, 5, 6, 7, 8. So the carbon's happy. The oxygens have, remember these spots here represent electrons that are not being shared, but it is a pair of electrons. So we have 2, 4, 6, 8. 2, 4, 6, 8. Everybody's happy. And it forms a double bond. Okay? Now there's one more very important concept that we need to talk about in this section, and that is polar and nonpolar. Okay? And the page talks about polar and nonpolar bonds and polar and nonpolar molecules. All right, let's see if we can do this. Let's go back to, let's put a chlorine with a hydrogen. Okay? So chlorine is 7. 1, 2, 3, 4, 5, 6, 7. Hydrogen has 1. Okay, so it forms one bond right there. Which of these atoms is actually more like the big burly high schooler that's just pulling on that electron the hardest? Do you know?
The chlorine?
The chlorine. If we look at the periodic table, the elements further over this way are the bullies, okay? They're the big high school bullies. The elements over here, okay, are weaker in general. Now your PACE actually has a chart, and that is on page 8 at the bottom. And it has numbers, okay? So the element that has the bigger number, it's like measuring the strength to try to pull the electron toward it. So just like the bully here is pulling the electron, so even though they're technically sharing the ball is spending more time around the bully than it is around the weakling. Okay? If it were two girls sharing a doll, okay, a 4th grade girl and a little 4-year-old girl, they might be saying they're sharing the doll, but I guarantee you the 4th grader is going to have the doll in her possession more, okay? Because she's bigger, she's stronger. So so that number measures the strength of how strong that atom is saying, I want that electron around me. So looking at this bond right here, chlorine is a bigger bully. So it is saying, I want that electron closer to me than to you. So in this bond, this would be slightly positive or slightly negative?
Negative.
Good. I started writing a positive, but slightly negative. This would be slightly positive. So this is the bond. Now we can have within this molecule, which is stronger, the oxygen or the carbon? I actually have to look on here to see because they're pretty close to each other. Let's see. Oxygen is 3.4, carbon is 2.6. So the oxygen is actually the bigger bully. So it's going to be a little more negative here, a little more positive here, a little more negative here, a little more positive here within that bond. So this is a polar bond. Now the PACE points out if two atoms that are exactly the same are sharing an electron, like two hydrogens, then we say it's a nonpolar bond, okay? Because it's exactly the same. Oxygen, two oxygens actually can share electrons, all right? They're going to form a double bond between them and have 1, 2, 3, 4, 5, 6, 7, 8, all right? But because they're exactly the same element, neither one is stronger than the other, like twin sisters. So they have exactly the same strength, so we say this is nonpolar. Polar means you have a slightly positive or slightly negative zone. So that's the bonds. Now let's talk about the molecule itself. Okay, let me get a different color here. I'm going to grab the blue. And let's start with this one, okay? Hydrogen by itself was neutral, chlorine was neutral. But when they share this electron, the negative electron spends more time in the possession of the chlorine, which means this zone over here is slightly negative, okay, because electrons are negative. So we use a symbol that's called delta. It's the Greek letter delta. And we do delta negative to mean this zone is slightly, it's not like an ion where it's definitely +1, -1. It's just slightly negative. And then this zone on this molecule would be slightly positive. Okay? So did I make one of those? So that would be kind of like chlorine. Oh, let me choose a different color for chlorine. Let's say chlorine is blue, okay? And then the hydrogen. So this zone would be slightly negative, this zone slightly positive. So when it interacts with other molecules, it might orient itself, kind of like magnets, you know, like the like side of a magnet will repel, the two north ends will push away. So if I had another molecule similar to this, it would, you know, try to orient itself so that the slightly negative is near the slightly positive. What do you think happens with the water molecule? Is this a polar molecule or nonpolar? It is going to be polar because they don't share the electron easily. Which one do you think is the bully?
Oxygen.
Oxygen is the bully, okay? So on this molecule, this zone around the oxygen is going to be slightly negative. And around the hydrogens here, it'll be slightly positive, kind of like happened here, okay? Slightly positive. Now that's really cool with water, and the PACE talks about this. This is very important. This is the hydrogen bonding. When water molecules get near each other, they don't want to get together like this because they're the same charge. And so they'll arrange themselves in different ways so that the slightly positive will be near the slightly negative. Now it's not like a molecular bond that holds them together tightly, but holds them close enough to each other that they kind of roll around. That's what makes water a liquid at room temperature, okay? So that we can drink it and pour it. If it did not have that property of being attracted to other molecules, it would actually fly apart and be a gas, and there would be no water. The only way you could get water would be to get the temperature, you know, really below zero before they would finally get close enough to each other to form a liquid. So in God's wisdom, all right, He designed the hydrogen bonding to be strong enough that it keeps the water molecules near each other. And then when it freezes, they actually, and your PACE shows this, they form a crystal, so they actually spread out. And that causes them to float on top of lakes and ponds rather than sink and kill all the fish and everything in the pond. It floats. Again, sustaining life. It's the only substance that does that. Everything else gets smaller when it freezes. Okay? Now, let's talk about, so this would be a polar molecule. Let's talk about this one, carbon dioxide. Was this carbon dioxide? Carbon dioxide. These bonds are polar bonds, right? Is this a polar molecule or nonpolar?
Wouldn't it be nonpolar because the two oxygen are sharing?
It's nonpolar because this zone and this zone are exactly the same as each other, okay? Now they're slightly negative compared to this, but they're not, they're the same compared to this molecule, okay? So the molecule itself is nonpolar, and they line up. You can see in this thing why they're in a straight line. We call this linear or line, and that's why they are nonpolar. So again, your PACE shows a picture of it flat, and it's hard to visualize that, so that's why I wanted you to see this model, is so hopefully you can see that it is in three-dimensional lined up like this. Okay? So a polar molecule. What about this one? You think this is polar or nonpolar? These are all hydrogens. This is a carbon in the middle.
Nonpolar. Nonpolar.
Very good. Nonpolar. Again, the bond between this and the carbon is polar, okay? But this zone, this zone, this zone, and this zone in relation to each other are all exactly the same. So this molecule is nonpolar, okay? Polar means there's one zone that's slightly positive while there's another one that's slightly negative. And in this one, they're all the same as each other. Does that make sense? Okay. All right. I think we covered everything that we needed to. The polar, nonpolar. We can tell by looking, if we take two atoms and put them together, which one is stronger by looking at the numbers. This is the measure of their strength to try to hold that electron. And then over here is where it talks about the hydrogen bonding and why that's so important and why water is different than everything else. Okay, so we'll stop the video here and trust that that will help you do well on your checkup and your homework and your coming up self-test.